Welcome, everyone. If you've ever picked up a welding rod and wondered what those numbers and letters stamped on the side really mean, you're in the right place. Today we're breaking down SMAW electrode nomenclature for carbon steel, alloy steel, and stainless steel, all in one video. By the end, you'll be able to walk into any welding supply store and pick the exact electrode you need, every single time. Let's start with the basics. What is SMAW and why does the electrode classification matter so much? SMAW, shielded metal arc welding, is one of the oldest and most versatile welding processes in the world. You've probably heard it called stick welding. A consumable electrode, coated with flux, is clamped into an electrode holder. When you strike an arc, the electrode melts into the base metal, and the flux coating burns to create a shielding gas that protects the weld pool from atmospheric contamination. Now, the classification system for SMAW electrodes is standardized by the AWS, the American Welding Society. And the classification tells you the tensile strength of the deposited weld metal, the welding positions it can be used in, and the type of coating and current it uses. Let's dig in. Carbon steel SMAW electrodes follow the AWSA 5.1 specification. The designation looks like this: EXXXX. Let's decode it letter by letter. The E simply stands for electrode. Every SMAW electrode starts with this letter. The next 2 or 3 digits indicate the minimum tensile strength of the deposited weld metal in thousands of pounds per square inch, KSI. So E60XX gives you 60,000 psi tensile strength. E70XX gives 70,000 psi. E80XX gives 80,000 psi, and so on. The second to last digit tells you the welding position. 1 means the electrode can be used in all positions: flat, horizontal, vertical, and overhead. 2 means flat and horizontal only. 4 means it's optimized for vertical down welding. The last digit is critical. It tells you the type of flux coating on the electrode and the type of welding current you need. Let's look at the most common ones. Let's go through the most commonly used carbon steel electrodes in the field. E6010, E60KSI tensile, all position, cellulosic sodium coating, DCEP only. This rod is famous for its deep penetrating arc and fast freeze slag. It's the go-to for pipeline route passes and dirty or rusty steel. It only runs on DC positive. E6011, nearly identical to E6010, but the potassium in the coating allows it to run on both AC and DC. This makes it ideal for field welding where AC machines are common. E7018. This is probably the most popular low-hydrogen electrode in the world. It runs on AC or DCEP, deposits a smooth bead with excellent mechanical properties, and is required by many codes for structural and pressure vessel work. The iron powder in the coating gives a high deposition rate. Remember, these must be stored in a rod oven at 250 to 300 degrees Fahrenheit to prevent moisture absorption. For low alloy steel electrodes, AWSA 5.5 adds a suffix after the standard carbon steel designation. The format becomes EXXXX, A1, B1, B2, C1, D1, etc. That suffix tells you the chemical composition of the alloying elements in the deposited weld metal. Let's look at the major suffix groups. Now let's go through each suffix group in the table and understand what they actually mean in the real world. The A1 suffix stands for carbon molybdenum. It contains approximately 0.5% of molybdenum, which improves strength at elevated temperatures. You'll find A1 electrodes used in boiler tubes, steam piping, and other components that operate continuously at high heat. The B series, B1, B2, B3, B4, B6, and B8 are all chromium molybdenum, or CRMO alloys. As the number goes up, the chromium content increases. B1 has 0.5% chromium. B2 has 1.25%. B3 steps up to 2.25% chromium with 1% molybdenum. B6 goes to 5% chromium, and B8 reaches 9% chromium with 1% molybdenum. Higher chromium content means better oxidation and creep resistance at extreme temperatures. These are your refinery, power plant, and pressure vessel electrodes, applications where the metal must hold its strength at temperatures that would cause ordinary carbon steel to fail. The C series, C1, C2, and C3, are nickel steel alloys. Instead of going up in temperature resistance, nickel does the opposite. It improves toughness at very low temperatures. C1 has 2.5% nickel. C2 has 3.25%. C3 uses about 1% nickel along with small additions of chromium and molybdenum. If you're welding cryogenic storage tanks, LNG pipelines, or any structure that will operate below -40 degrees Fahrenheit, the C-series electrodes are what you reach for. The D series, D1 and D2, are manganese-molybdenum alloys. Higher manganese content increases hardenability and strength. D1 electrodes were historically used for welding high-80 steel, a high-yield, high-toughness steel used in naval and military armor plate applications. Finally, the G suffix is a catch-all category. It means the electrode contains at least one alloying addition, but only one element needs to meet a minimum requirement. The G designation is essentially a flexible, general-purpose category. Whenever you see a G suffix, always go directly to the manufacturer's datasheet to understand the exact chemistry and intended application. One important note: all of these low-alloy electrodes are low hydrogen types and require the same storage discipline as your E7018. Keep them in a rod oven, and always preheat the base metal according to your welding procedure specification. Skipping preheat on crossing SMAW pipe is one of the most common causes of hydrogen cracking in the field. Take E8018B2. E. Electrode. 80 to 80,000 psi minimum tensile strength. 1. All positions. 8. Low hydrogen iron powder coating, AC or DCEP. B2. Chrome moly alloy, 1.25% chromium, 0.5% molybdenum. This electrode is widely used in petroleum refinery piping and high-temperature pressure vessels. Preheat is critical with these alloys. Always check the WPS. Stainless steel SMAW electrodes follow a WSA 5.4. The designation format is EXXX, L or HXX. This looks a bit different from carbon steel. Let's break it down. The three-digit number after E refers to the stainless steel alloy designation. You'll recognize these from the IC stainless steel classification system. 308 corresponds to 304 base metal. 309 is used for dissimilar metal joins, carbon steel to stainless, or as a buffer layer. 310 is for extreme high-temperature applications. 316 adds molybdenum for better corrosion resistance in chloride environments, marine and chemical service. 347 contains niobium, columbium, for stabilized grades, used when post-weld heat treatment isn't possible. After the alloy number, you may see an L or an H. L means low carbon. The carbon content is limited to 0.04% maximum. This is used to minimize carbide precipitation and intergranular corrosion, critical in service environments where the weld will be exposed to temperatures between 800 and 1500 degrees Fahrenheit. H means high carbon, minimum 0.04% carbon, used specifically for high temperature creep resistance in service above 1000 degrees Fahrenheit. So E308L is your standard choice for welding 304L base metal, and it resists sensitization without post-weld heat treatment. The two-digit number after the hyphen describes the flux coating and current type. For stainless steel electrodes, the most common are -15, lime, basic, coating, DCEP only. Excellent in all positions but produces a stiffer arc. -16, titania potassium coating, AC or DCEP. This is the most common and versatile. Easier arc control, good for all positions. -17, silica titania coating, AC or DCEP. Smooth bead, flat profile, used mostly in flat and horizontal. Let's decode a full stainless steel example. E316L16. Electrode, 316, alloy type, 18% chromium, 12% nickel, 2% molybdenum. Low carbon, max 0.04% C-16, titania potassium coating, AC or DCEP, all positions. Use case: welding 316L stainless steel piping in a pharmaceutical or seawater service application. The molybdenum adds pitting resistance against chlorides, and the low carbon prevents sensitization. Now that we've covered all three electrode families in detail, let's bring them side by side so you can see exactly how the designation systems compare with each other at a glance. All three families start with the letter E for electrode, that part never changes. But from there, the systems diverge. Carbon steel electrodes under a WSA 5.1 use a 4-digit format, EXXXX. The first two digits give you minimum tensile strength in thousands of psi. The third digit is welding position, and the fourth digit codes the flux coating and current type. Simple and compact. Low alloy steel electrodes under a WSA 5.5 use the exact same 4-digit base as carbon steel, same tensile strength digits, same position digit, same coating digit. The only difference is what comes after the hyphen. That suffix, A1, B2, C1, D1, and so on, is where all the alloy chemistry information is stored. So if you already understand carbon steel electrode nomenclature, reading a low alloy designation is just one step further. Stainless steel electrodes under a WSA 5.4 are structured differently. Instead of tensile strength digits, the number after the E is a 3-digit stainless steel alloy type, 308, 309, 316, 347, which you'll recognize from the IC stainless classification system. Carbon content is called out explicitly with an L for low carbon or an H for high carbon. And the coating and current information comes as a 2-digit suffix after a hyphen, 15, 16, or 17, rather than a single digit like in carbon steel. Notice also that stainless steel electrodes don't have a dedicated position digit in the same way. Position capability is determined by the coating type. The -15 and -16 coatings handle all positions, while -17 is generally limited to flat and horizontal. One more key difference: carbon content. In carbon and low alloy steel designations, carbon content is not called out in the electrode name at all. You need to look at the data sheet. But in stainless steel, carbon content matters so much for corrosion performance that it's right there in the name. The L and H suffixes are a built-in reminder to think about sensitization and service temperature before you strike an arc. So when you're standing at the welding supply counter, here's the quick mental checklist. What is my base metal, carbon, alloy, or stainless? What tensile strength or alloy match do I need? What position am I welding in? What current does my machine put out, AC or DC? Answer those 4 questions, and the electrode designation system will point you directly to the right rod every single time. Before we wrap up, here are some critical pro tips that will save your welds. Tip 1. Low hydrogen storage. E7018, E8018, and all low hydrogen electrodes absorb moisture from the air within hours of opening. Always store them in a rod oven at 250 to 300 degrees Fahrenheit, 120 to 150 degrees Celsius. Wet rods cause hydrogen-induced cracking, a silent killer in structural welds. Tip 2. Preheat for alloys. All low alloy electrodes, especially SMAW types like B2, B3, require preheat. Check the WPS and ASME, AWS code requirements. Skipping preheat causes cracking in the heat-affected zone. Tip 3. Match your filler to your base. Don't use E308 on 316L base metal. Use E316L. The extra molybdenum in 316 is essential for corrosion resistance. Mismatched filler is a common and costly mistake. Tip 4. Current and polarity matter. Using an AC electrode on DC or the wrong polarity can cause arc instability, spatter, and pore fusion. Always read the electrode spec sheet before striking an arc. And that's SMAW electrode nomenclature decoded, carbon steel, low alloy steel, and stainless steel, all in one video. If you found this useful, smash that like button and subscribe. We post welding education videos every week. Drop a comment below with your favorite electrode or any questions you have. If you want a downloadable PDF reference card of these electrode tables, check the link in the description. Thanks for watching, and happy welding!